Okay, I have the homework problem 13.22. Now this is a reaction where a gas is splitting into two other gas particles. Now, unlike the example in class, where we were able to get the partial pressure of the reactant as a function of time, this one is a bit different. It gives us the total pressure in the container as a function of time. And so the total pressure is not just the pressure of the individual reactant ClCO2, CCl3. It's also the pressure of the COCl2 added in. So we're going to have to do some back calculating to get the pressure of just the reactant ClCO2, CCl3. Now for time 0, before the reaction has occurred, the pressure in the container is the pressure of the original gas, ClCO2, CCl3. It's 15.76 millimeters of mercury. And the pressure of the product is 0 because it hasn't had time to react yet. And so the total pressure is 15.76 plus 0, 15.76 millimeters of mercury over here. Because P total is the reactant plus the product pressure. Dalton's law of partial pressures. However, after the first 181 seconds, we will say that we have lost X amount of the reactant while gaining, look at your stoichiometry, 2X amount of the product. So as a result, our pressure goes up from 15.76 to 18.88. Now, if we're able to calculate what that means, basically it's the original pressure, 15.76, minus X, the amount of the reactant that reacts, plus 2X, the amount of product that forms. So if you do the algebra on that, that becomes 15.76 plus X. So in other words, 15.76 plus X equals 18.88. So working it out for X, I get that the X equals 3.12 millimeters of mercury of the original reactant has reacted. So 3.12 millimeters of mercury has reacted by 15.76 is now dropped down to 12.64. Now just to double check my math, that means that the COCl2 has jumped from 0 to 6.24, 2x. And now if I add these two pressures together, I do get the pressure they give in the problem, 18.88 millimeters of mercury. So then repeating that math for the third and fourth time that was given, we end up getting 8.73 millimeters of mercury left over for the reactant at 513 seconds and 4.44 millimeters of mercury left over at 1164 seconds. So now to graph the data to see what the order of the reaction is, I need to graph the pressure versus time for the reactant and see which one gives a straight line. Now, I'm not going to graph it on the board, but instead what I'm going to do is I'm going to take some ordered pairs and find some slopes and see if the slopes are constant. If the slope is constant for the data, that means it is a line. So if I take the difference between 15.76 and 12.64, 3.12, divide by the difference between 0 and 181, then I get a slope of 0.0172 if I were to graph pressure versus time. However, for the second two data points, 181 and 513 for the second and third data points, I would actually get a difference between these two numbers of 3.91 and a time of 332 seconds, which gives me a slope of 0.0118. So it looks to me like my slope is decreasing. So that means my graph would look something like this, right? So it's going to be a decaying curve there. So that tells me I don't have a zeroth order. So the next thing to try would be, is it a first order? So for a first order reaction, remember that we graph natural log. So I'm going to take my pressures and try graphing the natural log of pressure. So the natural log of 15.76 is 2.76, 12.64 is 2.54, 8.73 is 2.17, and 4.44 is 1.49. So now I have 4 times and 4 natural logs of pressure. I could use the graphing calculator or Excel program and graph it, or if I want to tell if it's a straight line, I could see if the change in y equals the change over the change in x equals a constant. So I take this difference, 0.22, divide by this difference, 181, I get a slope of 0.0012. This difference divided by this difference gives me a slope of 0.0011. This difference and this difference gives me 0.0010. So I'm really staying right around that slope of 0.0011. And so we're going to call it first order. And remember, the slope is the k. Actually, these slopes are negatives, and so the slope is negative k. But as a result, I can actually get the slope from this information that I did here. I'm going to round it to 0.0011. And with the first order reaction, the unit would be seconds to the minus 1. So that's how I did that one. It's a very complicated problem because of all this extra math you have to do to figure out the initial pressures, and not just the initial, but all the pressures of the reactant.